Hello everyone. Today Victor is going to tell us about Frobenius algebras and complementarity.
Yeah.
Please take it away.
Okay. Oh, what? First, well, thanks everybody for coming. To start the talk, I would like to give some motivation because Frobenius algebras were first defined in the context of basic algebra, commutative algebra. Is it working? Can you hear? Okay. Okay, so for instance, let's recall some basic notions of algebra for a commutative ring R with identity, of course, monoid object in this symmetric monoidal category, the category of R models, okay, is an R algebra. I.e., well, a triple where, of course, A is an R model, U is the product, and eta is the unit. Okay. Well, this is. Everybody here is familiar with the notion of commutative rings. Maybe a short reminder. Well, a commutative ring R is a generalization of a field. Well, a field is, for instance, R, complexes, rationals, etc. So, for example, Z is a ring, the integers. Z squared, the lattice, is a Z model. So another model is a generalization of a vector space. Another example, okay, a more interesting one. The integers modulo 2 is also a Z model. Remember, this is just a set with two elements, and where the sum is defined in this way. Well, which is natural, of course. But here we have something different to the real case. Okay, the integers modulo 2 is a Z model. Okay. The example of an R algebra. We can give this example. The ring of polynomials. Yes, this is an example of infinite dimensional R algebra, or we can give another example. Truncated polynomials that now is finite dimensional. Now, a common object, common object, or just common in the same symmetric monoidal category is called an R algebra, coalgebra. Okay, let's give an example. Let's suppose that R is in this case a field, like reals, complex, or rationals. Okay, a field. Let's suppose that A is a finite dimensional algebra, K algebra. When I say finite dimensional, I mean as a K vector space. The dual space defined as this way is a coalgebra. Another example of a coalgebra. Let's suppose that B is a vector space over K. We are going to define, I don't remember the name of this. It is the tensor algebra, tensor coalgebra, depending on what part of the structure you are interested in. Is a direct sum where, oh, sorry. Just to clarify, when K is 0, it's just the field K, and of course, K is 1, this is just B. Okay. Oh? Yes. Right. Yes. What R? Okay, sorry. Yes. Okay, but the importance of this example is that this is both an algebra and a coalgebra. When we have this situation, we just say this is a B algebra or bi algebra. I don't know. Bi algebra. Thanks. Sorry. Well, we have saying that A is an R. Yes. Is it the same thing as saying A is a commute? Yes. An algebra is itself a ring. Yes. Yeah, but because from this structure, yes, exactly. Yes. But might not be a commutative ring anymore. A. I will give another example. Yes, it depends. So, yes, I just said an algebra. A is itself a ring. But let's give an example of non-commutative ring or non-commutative algebra. Okay, the group ring. Let's suppose that G is a finite group. We define this group ring, or somebody might call it a group algebra. It's a set of formal sums where coefficients in a complex field are what G is an element of capital G. Yes. So there is a product for G in G, H in G2, defined by the following. Well, CK is this sum of products, where G times H is K. Okay. So at least when G, well, this definition makes sense even when G is not finite, but at least when G is finite, this is a finite dimensional algebra. Now, an observation. Remember, this guy is also a ring, but is not commutative or non-commutative. If G is not abelian. Or non-abelian. Well, okay. Now we are almost ready to define the notion of a Frobenius algebra in the context of basic algebra. Then we will generalize it for general symmetric monoidal categories. Okay. Well, just analogously to the definition of an algebra, a coalgebra is a triple. Remember, where delta is a homomorphism from A to A tensor A, and epsilon is the co-unit. Okay. Now, okay. Now we can talk about a Frobenius algebra. Frobenius algebra is a K vector space with an algebra structure A mu eta and a coalgebra structure A delta epsilon, such that this equation is satisfied. identity, okay. Identity. Okay, so the algebra structure and the coalgebra structure are somehow compatible by this equation. And more graphically, we have the following. Well, we have a convention for the product, the coproduct, but in a suggestive way, I will use this notation for the product and the coproduct. Well, this is again the identity. Okay. This another is an alternative. Yes. I will explain what it is. This is a way to denote eta. Well, this of course the identity. This is the product. It's like we have A, and A here. This is the counit. Oh, well, this is again the identity. This is the coproduct. Okay, this will be important when, if we have time, I would like to talk quickly about Frobenius, topological quantum field theory. So I introduce this in a suggestive way. So in general, more generally, we have the following definition. In a monoidal category, Frobenius structure is a pair given by monoid Now, this is our convention, right? And monoid satisfy the Frobenius law. Okay. Okay. Okay, this is the standard notation we are following in the seminar. Okay, but there is also an interpretation with this notation. Well, some people use this other equality as an action, but it can be shown, in fact. Oh, hi. Well, in fact, this equality implies these other two equalities. Well, let's give some examples. Examples of Frobenius algebras. Okay, for instance, finite dimensional Hopf algebras. Well, maybe it's we don't know what a Hopf algebras is, but maybe you're familiar with cohomology rings. We can take the cohomology ring of a compact Lie group. Compact Lie group. Well, as this is a cohomology ring, it has a natural algebra structure, but we can also define a coalgebra structure. We can define a coproduct by using the product of G, because as the cohomology is contravariant, we have this homomorphism, but this is isomorphic to the tensor product of cohomology rings. Right? Okay. So a Hopf algebra, finite dimensional Hopf algebra has a Frobenius algebra structure.
Isn't that the group algebra is a good example?
Oh?
The group algebra is
This is a simple example, yes. The group algebra is another example. Oh, right. This is in my notes too. Another maybe sample, the rank homology. PR of X, where X is n-dimensional, compact, oriented manifold. But of course, a simpler example is given by the group algebra. Another example is a Frobenius algebra. Well, we need to define the product and the coproduct. Well, the group ring makes sense for any ring. Sorry, we don't have to restrict to the complex field. We just extend this map by linearity, and the coproduct is defined in this way: gh minus 1 tensor h. Sorry, everybody here knows the notion of a group, right? Okay, great. Well, in principle, a group is like, we can think of the set of permutation of n letters. G is, if at least if G is finite, it's always a subset of sigma n, satisfying some group conditions. Well, we can also define eta times S to S1G and epsilon G to 1 if G is the identity and 0 otherwise. Okay, any questions so far? Maybe when you were just saying it's an alternative, but also it's a suggestive way to connect this with topological quantum field theory, because we can see that topological quantum field theories, the category of topological quantum field theories, is equivalent to the category of commutative Frobenius algebras, at least for two-dimensional case. It's another alternative. Okay. Duality. Okay. These are theorem in a monoidal category. If A has a Frobenius structure, then A is the dual of A. We remember the notion of duality, but there is a notion of duality. We say that, L is the left dual of R, and R is the left dual of L. In this case, in a Frobenius structure, A is its own dual. And this theorem implies the following proposition. There is a bijective correspondence I hope to have a space. Let's see. Monoids. Making the pair into a Frobenius structure and the set of morphisms from A to the identity, making the composite this composite the cap of self duality. Now, the definition I gave for Frobenius algebra is due to Lover. I mean, I don't know if I pronounce this guy, but the kind of algebras Frobenius was interested in was essentially given by this definition. Frobenius structure. Yes. Frobenius structure. A is its own dual. But generally, there is a theory of duality, right? Well, two objects are A is self-dual, right? Yes, exactly. Well, I guess isomorphic, I guess. How much time? Huh? Oh, okay. I think I have more examples of this. Oh, okay. Okay, as I said, this is, thanks to this proposition, we can see this set of morphisms together with this monoid structure, an alternative definition of Frobenius structure. And that's exactly the kind of algebras Frobenius work. And that's why the origin of the name. Okay, apparently. Exactly, because what is the definition given by Frobenius originally? Let's suppose we have A is an algebra, an R algebra. A is Frobenius if and only if A is isomorphic to its dual as an A model. Because A is also a ring. So it makes sense, this definition. Oh, well, we should be careful because here we are studying A as a left E model. and the dual of A as a right A model. Yes. So this is the other equivalent definition of a Frobenius algebra. Of course, in the context of basic algebra. Yes. Well, apparently I skipped some definitions. Sorry. So we already know the definition of monoidal dagger category. Monoidal, I will write it properly. Dagger category. Okay. We say that this Frobenius structure is dagger if the coproduct is the dagger of the product and the counit is dagger of the unit. So at least in monoidal dagger categories, the monoid structure induces the comonoid structure. Okay.
We have a dagger structure, right? So if I have a monoid structure, if I find the dagger, I get a comoid.
Okay, I think it's not so simple, but I don't. F help, yes, but
The comoid you get because dagger goes to the opposite category, so monoid.
hmm,
So you automatically, by applying the dagger, get the comoid data from the monoid. So the compatibility is unique.
Well, the compatibility is these are duality. For instance, you can have dimension field. You cannot have duality. You get covalent structure.
yes. So at least in monoidal dagger categories, we can concentrate in the monoid category structure to give a comonoid structure. Well, okay, in a general monoidal category, pair and a monoid structure. No, this is yeah, monoid structure and comonoid structure is special when we have this situation. Uh, or in other words, Ah,
A condition, yeah.
right, sorry. Okay, so coproduct is a left inverse of product is a left inverse of the coproduct. Okay, yes. So with this terminology, we can define a classical structure. Classical structure is a dagger, Frobenius structure that is both special. Well, we know what a commutative monoid is and a co-commutative comonoid is, right? It's quite natural. So we can also speak of a commutative Frobenius structure, assuming that both the monoid and the comonoid structure are commutative.
The term classical structure coming from quantum theory, or is the term in algebra?
No, it's part of the quantum theory. Yes.
This is a Vicary
Vicary. Yes, part of the book. At least in the case of F Hill, uh, it's classical because somehow it's a trivial structure. We will see why. Yes.
But it's special.
Uh, Sorry, we have a clear idea of what a commutative monoid is and a commutative comonoid. Okay, just to give an example of this thing, uh, remember our examples of the group algebra. Let's suppose the group rig of C2 or Z mod 2 is this ring of truncated polynomials. And if G is the group of abelian group of integers, this is the ring of Laurent polynomials. So they are commutative algebras and commutative coalgebras because the group inside is abelian. That's why.
But the second is not
No, I just wanted to give you an example of a commutative monoid. Commutative algebra, sorry. Example of commutative algebra. Yes. Okay, an example of special structure. A groupoid bold G induces a Frobenius structure in a REL. Okay, let's give explicitly the structure GF, G compose F, when the domain of G equals the codomain of F, the unit, sorry,
So G is a groupoid.
a groupoid,
Uses a Frobenius structure.
real, the category of relations.
Yeah, okay. What do you mean it uses a Frobenius?
Actually, equivalent. Frobenius structure.
Right. Yes, this is a result. Yes, but any Frobenius structure in real is a groupoid, essentially.
So the set that carries the structure is the set of morphisms.
On the set
Exactly.
of
That's where I was getting to.
all morphism
I'm looking at operations.
of G-bolt. Yes, on this set. Yes. This is a unit. X is an object of G-bolt. So yes. So this Frobenius structure is always special. But is commutative if the groupoid is abelian. Okay. F compose. Right?
That's not a condition you can always impose. It's tricky to say.
When they are composable. Yeah. Oh, why?
If F and G are composable, that doesn't mean G and F.
Right.
You can say, well, you can say G is an abelian group, and then
Yeah, so like in the special case of one object groupoids, then this is true. The condition that you want in this case is that so not just if G is abelian, but if G is abelian and every time G and F are composable, F and G are composable.
Okay.
Which tells you that G is a disjoint union of one object.
That's true. Yeah, that was more complicated than my first impression. Okay. Thanks. What? Eraser? Now, well, after all these previous definitions, we can say something about our favorite category. Theorem. Buddy, which is our favorite category? F Hill.
my favorite is red.
Oh, okay, sorry. Oh, well, let's, well, I mean, an object in this category, then there is a bijective correspondence between orthogonal bases of A, respectively orthonormal bases of A. I need another marker. Well, seems to be better. And commutative dagger Frobenius structure on A, and respectively classical structures on A. I think I have the correspondence here. Okay. Remember, as this is a dagger Frobenius structure, we only have to define it on the monoid structure. Maybe this one. Given this monoid structure, we can choose those vectors such that they satisfy this equation. Okay, this will be an orthogonal base, and if the yes,
Yeah, just not
the multiplication, yes. Well.
Yeah, when you know that it's open circle.
Okay, sorry, yes. It's
okay.
Yeah, I was following just the main reference, Heunen, Vicary. Yes. Well, I mean, this notation means this map, right?
No,
C to A.
C to A, sorry. Okay. Yeah, sorry. Have some. Okay, right. Sorry. You're right. Okay.
Oh, so my one was about when you use E and you're doing the multiplication.
Okay, yeah.
It means you denote it like build circles, whatever.
Sorry, what do you mean?
He's saying replace the black dot in what you've drawn in blue with an open circle.
Okay.
That's some other operation.
Right, yes.
Because you're not telling me what that is.
Yeah,
That's co-multiplication. Use that
this
notation,
co-multiplication, yes.
then it's indicative. Otherwise,
Yes, so sorry. Had to do. Remember that this monoid structure induces a common structure. Yes. Thanks a lot. Now, on the other hand, if we have a orthogonal basis, we send it to the following Frobenius structure. But this might be a bit weird. I write here as the I instead of AI, just to avoid overcharge notation. And also to follow Heunen Vicary notation. Right. Now the product given by okay. Yes, we are omitting, we are simplifying maybe too much the notation, but of course we have to add some decoration in this notation, maybe A here, etc. Okay. But at some point, the main reference forgets this and just simplify the notation this way. Okay.
I is an index, right? Or
No, I think you mean AI.
yeah, the AI and everything AI.
Okay, I can write it better here. Sorry.
Okay, I is a number.
I is the.
I is a natural number. What's the inner product of natural numbers?
Oh.
So
No,
all those should be
I should
AI.
write, in fact, AI.
Yeah, for everything.
Listen.
Yeah, but
Yes.
the book uses this precise notation.
Yeah, that's why I do this.
So if you write B as a set, you very often.
But there he wrote the one. I mean, I haven't read the book. I'm just reading what I see.
No, yeah, you're right, but it just
That's
instead of writing AI everywhere, the captain
just
bras
A.
are precisely AI.
Mm-hmm. Yes, to be more precise, when I draw this, I mean this edge, AI dagger, C, A, sorry, A, tensor AI, tensor AI. This is the dagger is the notation for this get or bracket, I don't know. Okay, yes, this is more properly what I mean with this notation. Is it more clear now? Yes.
Because you're writing sum over I.
Just notation, yes. Heunen Vicary is a bit confusing. Yes.
No, I know there's nothing. I can just write AI.
Well, any questions so far? Well, this was chapter 5 of Heunen Vicary. Now, chapter 6 is on complementarity. Now we are ready to introduce this concept. Okay, we're fine. Complementary structures. Definition. Let H an object it F hill. Two orthogonal bases AI and BI are complementary if there exists S, a complex number, such that this product of inner products equals S always for every I and J. An observation: within each basis, the elements of the basis have a constant norm, and this is because thanks to this condition we have the following. Well, this equality is just linear algebra, and by hypothesis we know this have this, okay, with this S, the same S. Okay, and similarly for the other basis. Similarly for this inner product. Okay, now we are ready to define the notion of complementary Frobenius structure. In a symmetric monoidal category, two commutative dagger Frobenius structures given by the product. I hope this is not confusing. They both are products in this case. I'm following the reference, sorry. On H, okay, I will write this. Products. No, They both are products. And we are considering dagger Frobenius structure. It's enough to give two products. Then we can induce the coproducts. Okay, are complementary? If okay, I need some space. Okay. I'm not omitting anything. I hope so. So these equations are satisfied.
Which is the circle at the top? The circle at the top should be at the intersection rather than, like, what you draw on the left has
Here?
one input and no output.
Yeah, yeah.
Whereas what you draw in the middle has one input and one output.
Ah, okay. Maybe I am omitting something.
No, I mean, you'll either have a circle or a filled circle at that threefold intersection, but none at the very top.
Ah, okay.
Yeah, I just flip it and then.
Sorry, you mean?
Yeah, just put a black dot at the.
uh,
No,
the-
no, just right there.
Ah, okay. Ah, okay, sorry. Thanks. Ah, I had to. Okay. Oh, but this is exactly the other side. Let me check. Well, the other side, according to Heunen Vicary, is this thing. Yes. Okay. Hmm. Yes, some.
Just by symmetry.
Yeah, because so in both cases, the white thing is the bottom. It's about switching the order.
Yeah, now that you say yes, it's true. Or maybe it was a typo in the book. Oh, well. Yeah, to be honest, it was also confusing to me. But the nice result from this is the following. Okay. Again, let H be an object in F hill given to commutative dagger Frobenius structures on H. The following conditions are equivalent. Oh, no, the following. No, the following situation, let's say. The following two sets as Frobenius structure, they are the following condition. They are complementary and as basis, because remember this Frobenius structure induces a orthonormal basis. as bases. They are complementary, but with S equals to 1. Yes. Remember, in this situation, we have the following. Dimension of H is always this thing. Yes. So this is how two complementary Frobenius structures are determined by the complementarity condition of the associated bases. So I have 1 hour and a half, or well,
You have 18 minutes left.
oh, great. So, well, in the rest, the remaining time, I would like to justify why the other alternative notation cover this end. Okay, let's denote by encode the category of coverdism. Coverdisms. Which are the objects? Are the close oriented and -1 manifolds, and morphisms are given by these manifolds M, where M is a oriented N manifold with boundary. Sigma is the in boundary of M. Sorry, sigma prime is the out boundary of M. Well, this is considered just up to diffeomorphism, rel the boundary. Yes. I just want to introduce this because this is another important context where Frobenius algebras are interesting.
What do you mean this is the independent boundary and this is the out boundary?
Ah, okay.
Right.
Well, let's suppose this is sigma, and this is sigma prime. Sigma. This is sigma prime. Well, this guy is M. So all this is a one manifold, one-dimensional manifold, and M is a two-dimensional manifold. Yes. So this is M. That's why the notation I used before. Yes, sigma is like a union of two circles.
I mean, this is, I think that it's not clear from what you've written that this is additional data that you're specifying. You're specifying not just a manifold boundary, but also a decomposition of its boundary into two disjoint
Ah,
sigma
okay.
and sigma 1, which you're calling in and out. It's not like,
it's because of the orientability, I guess.
no, it's still specifying data, like, which you call in and out, there is an induced boundary orientation, but then you're still choosing data in that you're choosing whether you're taking sigma with the induced boundary orientation or the opposite.
Okay.
If you choose this decomposition, it doesn't get inherited from the manifold. It's data or structure, not a property.
Okay. Thank you. You are the expert here. It's just something I just learned. Yes, but my intuition was that this is the in boundary in some graphical sense, and this is the out boundary, also in graphical sense. That was my picture.
Yeah. But the choices that is part of the cobordism.
Oh.
The cobordism isn't just a manifold with boundary, it's a manifold with some chosen data. You choose the decomposition of the boundary. So you know what its morphism from.
I see. Okay. Oh, great.
There are many other decompositions.
Okay. Thanks. Now, I hope this claim is correct. Ncom is a symmetric monoidal category. And disjoint, yes, exactly. A topological quantum field theory is a symmetric monoidal functor from N-cup to the monoidal category of vector spaces. Since, okay, they both are symmetric monoidal categories, it makes sense to speak of a symmetric monoidal functor between them. So that is a topological quantum field theory. Oh, okay, and dimensional. Yes.
I was wondering.
So, and dimensional quantum topological quantum field theory is the category of n-dimensional TQFT is just the category of symmetric monoidal functors, and some people denote this by Simon cut of n-cut and vect. Okay.
I mean, I would actually use fun with a superscript because in general, this would be the set of morphisms and fun would be the category. But it's completely irrelevant.
Yes, I'm here following just Joachim Kopp books. Now, in particular, if n equals 2, we can consider n2 Kopp as this category with objects 0, underline, etc., where n underline is the disjoint union of n circles. I mean S1. This is a one-dimensional manifold.
Can you go back to black?
I can use black. Okay. Okay, but let's see which one is working well. Okay, fine. Now, morphism in this category. Well, there is a generating set of morphisms given by these guys. Do you remember this? Additionally, we need this morphism. Okay. These morphisms encode the Frobenius structure. And this extra morphism encodes the commutativity. Well, these are the generating morphisms. And we can obtain all morphisms in this category by gluing this morphism with plus some relations that are given by the Frobenius law.
So what's the statement? Like, is like the free Frobenius algebra.
It is the free commuting, the free symmetric monoidal category on the free symmetric monoidal category on
Okay, now we remember that a topological quantum field theory is a symmetric monoidal functor from, in this case, from two vector spaces. And this guy sends the object 1 underline to a vector space and n to the tensor product. A will turn out to be a Frobenius algebra. So theorem, the category of two-dimensional topological quantum field theory is equivalent to the category of Frobenius algebras, commutative Frobenius algebras over K. Oh, this also over K. Yes.
This statement.
Yes.
Because the pub is sort of free, so symmetric monoidal function
Yes.
takes precisely the.
Yes, exactly. Okay. Now, okay. Yes. Well, I think this is the last result I was going to talk about. So that's all. Thanks for your attention.
Okay, thank you.
Okay.